We're going to start looking at calculus now, and there's two aspects to it. One, differential calculus, which is what we're going to start with, and then integral calculus, which we'll move on to in a few weeks' time. Differential calculus is probably the most important tool of mathematics applied to engineering that you'll come across, because it's a mathematics, a way of calculating when functions move. So when things change, then we apply calculus. And if you think about engineering scenarios, in circuits, AC circuits, we've got constantly changing voltages. In machines, we've got constantly moving machine parts. In gas and oil flow, water flow, we've got constantly flowing liquids and gases. Things move. And as soon as you want to model, in other words, try and come up with some function that describes how something moves, then you need to use calculus, differential calculus. A very, very powerful tool. Let's look at a function, y equals 3 sine 2 pi t. I could write this as vt equals 3 sine 2 pi t. So here is a function, and the notation could be like this. It could be a voltage function, or, in this particular example, a displacement function, s, where m is the variable. S is a variable measured in meters. And so it could be something like s t equals 3 sine 2 pi t. So I've got functions. I've got an independent variable, time, and a dependent variable, the variable that depends on the time, voltage, displacement, or just y. And traditionally we write the dependent variable on the y-axis and the independent variable on the x-axis. And we have that in our mind when we start thinking about calculus, because it's the way the dependent variable changes with the independent variable. So the notation's all about those two variables, x and y, or s and t, or v and t. Here's one function. We've sort of looked at it already today. We've looked at it in the past. A sine wave. And it's to do with the rotation, as we've discussed, around anti-clockwise like that. So something's rotating. Calculus tells us about the rate of rotation. The rate at which the thing's rotating, the rate at which it's being displaced up and down this y-axis in particular. So if I imagine this thing rotating around around in this direction, anti-clockwise in this direction, and we're only considering how it's moving up and down the y-axis, we can sort of imagine that it's going to start moving fairly quickly, and then it's going to slow down as it reaches the top, until it stops there and then carries on, starts going back down again, reaches a maximum speed in the y direction at the axis, and then carries on slowing down until it hits the maximum at the bottom where it stops, and so on. And if I want to know what the rate of change of displacement in the y direction this is showing, then I'm interested in what to do with this curve. What is it about this curve that tells me the rate of change of the function at a point? If I want to know the rate of change at a point, let's say this point here, what I'm actually after is the gradient, the rate at which the displacement, which is on this axis, is changing with time, which is on this axis, the gradient of the line. So the steeper the line, the greater the gradient, in other words, the greater the rate of change of this function. The gradient here is greater than it is here, and it's 0 here, and then it's greater here and greater here, and so on. And so I could zoom in on this axis using autograph at a point. So I'm interested in what's going on at 0.1 seconds. So 0.1 seconds on here was this point here. So I'm interested in what's the gradient at this point. So I use autograph, I zoom in, and here it is. And so now I can draw on here some convenient points. Let's try and take points where it almost cuts through a point. So there, it almost cuts through 2 points there, and it almost cuts through 2 points here. So let's use these 2 points here and work out the gradient. So I will say this point here is 1.768 from this axis minus 1.762. That will give me the length of that line. If I want the length of this line, it's 0.1003, near enough, and this point is 0.0999. And so I now do a little subtraction. 1.768 minus 1.762 is 0.006. Stop me if I go wrong. And 0.10, so 1003 effectively, if you take away 999, is 4, isn't it? So that's 0.0004. Is that right? Now to get the gradient, I divide y by x. 0.006 divided by 0.304. So it's like 4s into 60, which is 15. So I've taken my curve. This could be a moving machine part, and an engineer is interested in how fast is this machine part moving after 0.1 seconds. So I sketch the curve. I've been given this task. I use autograph, this fantastic software. I zoom in and I do this little calculation. I say it's moving at the rate of 15 meters, because I'm measuring the displacement in meters, per second, because I'm measuring the time in seconds. This machine part is literally moving at 15 meters per second after 0.1 seconds. I can get that information. Is that an exact answer? Is that the speed exactly at 0.1 seconds? You're shaking your head. Why? It's going to get more difficult. You just know it. You can feel it in your bones. Well, there's a mathematical reason why it's not exactly right, because I've zoomed in and I'm making a big assumption here, which is a reasonable assumption. And what is that assumption? It's a straight line, yeah. The more I zoom in, the nearer it is to a straight line. But actually, it's not a straight line, it's a curve. So it's an approximate answer, this, because it's a curve. I'm assuming that between 2 points, and it's a pretty good approximation because the software allows me to do it, I can come up with this. However, I'm going to tell you now that there is a way you can do it using differential calculus, which is even easier than this. It's a one-line calculation to be able to tell me what that speed is. And if that's not a powerful tool, then I don't know what is. A one-line calculation that you can go to somebody and say, oh, the speed at that point is 15 meters per second. Done. An immensely powerful tool. So I can find the gradient of this curve using something called differential calculus. The gradient gives us the rate of change of the function at a point. That's what the gradient means. For this function, y equals 3 sine 2 pi t, and this is where we start thinking in terms of notation. The differential, and it's called this, so let me just explain it. What it means written down is, it's the differential of y with respect to t. It's telling me the rate of change of the dependent variable, y, which in this case is s, the displacement, with, in this case, an independent variable of t, which is time. The rate of change of y by t. And we say it as dy by dt. So, dy by dt. It's like dy by dt. It doesn't mean d times y divided by d times d. It's not an algebraic expression, it's a notation. the differential of y with respect to t. And you're going to learn the rules for this. And they're straightforward rules. Once I know the rule, I can write down the answer. For this function here, 3 sine 2 pi t, the differential of y with respect to t is 6 pi cos 2 pi t. I can just literally write that down. There's no calculation. It's one line. So now, if I want to know what the differential at 0.1 seconds is, I just put t equal to 0.1 seconds in there, and out comes the answer. So if I want to know what the differential is at 0.1 seconds, I literally put 0.1 seconds into this differential function, get my calculator out and work out the answer. So if you just do that, and we get 15.2. The way calculus works is it actually effectively does this. It zooms in on the function. And as it was invented, the question was asked, what happens as the change in x and the change in y, this bit here, and it's called delta y over delta x, the change in y and delta x tends towards 0. What happens as delta y over delta x tends towards 0 was the question that was asked. And then you end up with a function that allows you to work out what that would be at 0. In other words, what's the gradient when that change is 0? An instantaneous, a point gradient, in other words. And if you do that, you end up with this function that we wrote down, this differential function here. Luckily for us, we don't need to do that every time, because for particular functions, that differential function is the same every time. So somebody works it out from first principles, what this function is, and then you just write down that solution in the table, and the rest of us, mere mortals, use this table to then work out the answer. That's why it's a one-answer solution. Really, it isn't. It's much more complicated than that to actually work out what it is. But luckily, it's the sort of thing you only need to do once. After that, you can just use it like a machine to put it into your calculator, and out comes the answer. In your textbook, it starts off with differential calculus by looking at differentiation from first principles. Have a look. See how it works if you're interested. If not, just take it as read, and we're just going to use those rules to find the differential function, as it's called. We can also use differential calculus to identify what are called turning points, maximum values. Remember we said at the beginning of today, what's the gradient when the function hits a maximum? Or a minimum, in fact. We find that the gradient is 0, and that's always the case. At maximum and minimum values for functions, whatever the function looks like, where it turns, where the gradient, and by turning I mean where the gradient goes from, say, negative to positive, or positive to negative, a turning point, or, much less likely, a negative to another negative, a point of inflection it's called, but we're not going to look at those in any great detail. These are the ones we're going to focus on. Points of maximum and minimum, turning points, can be found, because what we do is we take our differential function and find out the value of that when it's 0, because that's when the gradient's 0 when we have a turning point. So we'll see another great use of calculus is to find maximum and minimum values, which you can imagine for an engineering situation could be very useful. What's the maximum speed you're going to get? What's the minimum voltage you're going to get? Use differential calculus and find the value when it equals 0, when the differential equals 0. An extremely powerful